I'm Roberto Maieli from University Roma Tre, and it's a joint work with Matteo Acclavio, University of Denmark. And I mainly work on doesn't work.
Oh, now it should work.
Okay. Okay. So just this talk in one slide. I will present a proof search system, which is called Problem. It's a probabilistic linear object language program, and it's the main basic based on linear logic, which has been mentioned several times today, and is an extension of an original language program given by Jean-Marc Andrioli and Remo Pareschi, which is called linear object. And it is endowed with an internal probabilistic system, okay? And the main feature, the syntactical one, it's very simple. It's just a rewriting system. You have, you work with multi-set. So you have an head has been by multi-set of literals, multi-set of literals in the body, but take care at the comma, at the meaning. I will show you the meaning of this comma, and is endowed is noted with the probability. Okay, and what is interesting is the system, without relying on an external model, it is able internally to compute directly the probability computation of Bayesian network, something like that. Okay, very complex system, and exactly is able to express to represent complex Bayesian networks. The integration in logic programming is not trivial at all, because Bayesian networks are very complex directed cyclic graph equipped with probability distribution, and this system that I will show you is able to compute linearly joint probability and also marginal probability. Okay, and okay, so just recall some basic notion of probabilities. In this presentation, I will just talk about Boolean variable. Okay, so just what is a probability distribution? Is a function from a space of event to some values, of real values. Okay, so the event are x true, x false, just the two events that we have in our space. And the joint probability of the event is just the probability distribution of event x and n, and marginal probability is the probability of this event regardless of some other events. Okay, and then another notion, very logical notion, is the conditional probability of x1, xn given certain evidence. This means that which is the probability that I observed x1, xn given the evidence of y1, yn. And you can calculate this as a simple ratio between the joint probability and the marginal. And then what is very nice is the Bayesian law, the chain rule that says that you can factorize every joint probability as a product composition of conditional probability. Okay, and okay, what is a Bayesian network? It's a DAG, so it's a very direct and a cyclic graph, and every node stays for our Boolean variable, and every node is equipped with a table, a conditional probability table, which is saying what is the probability that wet is grass given the evidence that sprinklers are on and it's raining. Okay, so 99%. Okay, so what is interesting that this system it's just describe the behavior of a joint probability just in terms of the conditional probability of the conditional probability of one node given the evidence for the paths. This is the node, these are the paths. Okay. And okay. And then the Bayesian factorization says that every joint probability you can factorize as a product of conditional probability of the probability of a node given the evidence for the paths. For instance, assume this event that it's cloudy, sprinklers are on, it's raining, and the grass is wet. Okay, and then this joint probability is just given by the composition of this conditional probability, and the factorization reduces the complexity. Okay, it's still I mean it's a NP problem. Okay, it's an odd problem to compute the probability with Bayesian networks. Okay, and okay, so now if we try, this is a wrong solution, let's say. Okay, but let's go to a naive implementation. Okay, so it appears natural to think that a conditional probability I can associate a standard method in prologue side. Okay, annotated with probability, but where the comma is an additive conjunction. Okay, but then the problem is that this approach is not linear. We will not give, as I'll show you, the joint probability that we are looking for. So in this syntax, it's every conditional probability you can look at you can interpret the conditional probability as a method. Okay, so the condition that we were looking before, the wet is grass, given it's raining and sprinklers are on, it's 90%. Is the standard problem method. And this is the operational interpretation in terms of for people that work with the resolution, this is in a sequence style form. Okay, so we have the goal and then we split, and we can imagine, we can assume then the probability propagation is given by this kind of inference. But then the problem is that actually the joint probability in the Bayesian networks is a linear computation. But when you interpret in the standard prologue-like system or in intuitionistic system in terms of logic, you get something which is not linear because you duplicate the Acclavio. Okay, so this approach doesn't work, and the approach that we propose, which is based on linear logic, is to exactly think at just multi-step rewriting. Okay, where comma in the head is a disjunction, which is called the parallel OR. Okay, is the linear disjunction. But take care also in the value. The comma is not a conjunction, but is a parallel disjunction. Okay, and then the rules, the inference rules, is that is called in the focus system expansion rule. Is split in two parts. You have the left side where you compute the probability value, and the right part where you have the method, the program, and the multi-goal. Okay, so you match the head in the current goal, and then you just rewrite the system. So it's just a linear rewriting. You have no splitting at this moment. I will show you when splitting is necessary, when you work with marginal probability. Okay, so very simple system, completely based on operational semantics, but given by linear logic. Okay, and then our running example. Okay, the system will linearly gives you the joint probability. As you can see, just use this multi-head method at the last step, and derivation is just a trick. Okay, it's not branching, and okay, this is a linear computation. This is the idea. Technically, I will remind you to the paper, but I will show you practically what happened. Methods are in this form. Okay, so you can have multi-head with the body or without body in case that you have fat. Okay, and the interpretation is quite natural. A conditional probability of x1, xn given evidence y1, yn is exactly interpreted as a multi-set method where you have the literals capturing the meaning that x1 is true or false, and the meaning that y1, yn is true or false. Moreover, we need also a conditional distribution. So when we write a program, we need to collect some method in such a way that we have a conditional distribution. So we fix the body and we have to distribute with respect to the head. And the sum, every method is annotated with a probability, okay? And the sum of this probability has to be equal 1 because this is a conditional probability. In the case, this is the general case. In the case that we work with only Boolean variable, the conditional distribution is just given by a pair of methods because we have just the case that the head is true and the case that the head is so just two lines, okay? And what is a program is a set of conditional distribution, okay? And okay, that's the semantics. I remember we are talking about the proof search system, okay? And the state is split in 3 parts. You have the multi-goal on the right part, which has just literals, and the program, the multi-set of probability distribution, and the probability. The probability that this multi-goal will happen, okay? So it's a global probability. And okay, let's start from top and from bottom toward top. Okay, and this is a linear rules, which is called branching, which is associated with the width rules. Is an additive conjunction, and with it in this rule you perform the sum of the probability of the two branches. So when you have the branching, then you have the sum, not the product. You get the sum of a PQ, and this will annotate the probability of the conclusion. Okay, and then you have an expansion when you have the full method, the trigger, and you rewrite. It's just all the rules except the branching are linear. Okay, and you have also inside these rules a kind of mixed rule, just split when you have a fact, okay? So you have no body. In this case, you just separate this, you perform the expansion, stop. And then determination, when you consume, you have nothing. You have just one method and multi-goal that match perfectly, exactly with each one. Okay, so very simple system, and then when we encode the Bayesian network in this language, you take your Bayesian network, your DAG. Every DAG, every node has a certain number of parents and eventually some children. Okay, and what you have associated by definition in a Bayesian network the probability table, the conditional probability table, and in each row you have two methods that will be that will encode the two conditional probability. Okay, so you have the two methods, and the novelty is exactly given by the fact, because now the problem is that we have to compute the probability of the joint probability or the marginal probability, but at the same time we want to also check that we are working with a DAG. We have to check that it is a DAG, and we have to compute the overall probability of the DAG. Okay, and these two tasks we want to have performed simultaneously by the system, not separately. Okay, we want to perform proof search, and proof search make us sure that it is a DAG and the probability, the joint probability of all the DAG. Okay, so the method, as you can see in the head, there are some repetition, and this repetition is actually given by the number of children that match the children of the node that we are taking in consideration. Okay, so a certain number of occurrence for the head, and then the body that corresponds to the parents of objects. Okay, and the union of the conditional table for each node gives you what we call probo table, and the program is given by the big union of the tables associated with each node. Okay, and then okay, this is just the code that is associated. As you can see, just an example, in the case that you have the node cloudy, you have a proliferation of the head, okay? Because you have two children, but you also need an occurrence for matching the current goal when you perform your query. And then the truth theorem, the first one, which says that problem correctly computes joint probability. Okay, so we have soundness and completeness, and so we have a Boolean network with variable x1, xn, and this corresponds to the computation of the state, and the cost is linear. And now, as you can see, the joint probability of for instance, the event that is cloudy, rain splinters are on, and wet grass. Okay, this is linear, and the derivation is linear. And in red, you see the matching of the head that we use. Okay, and this is the power of parallel, or the path in a linear logic. Okay, this comma is exactly what was called today concurrency of a linear logic. Okay, and okay, and we are also able to compute correctly the marginal probabilities. The marginal is given, for instance, in this query. What's the probability that is cloudy, it's raining, wet is dry, okay? And in this query, we are marginalizing sprinklers, okay? This probability is given regardless of sprinkler. This means that we need to consider when sprinklers is false and when sprinkler is true, okay? So this the computation of this marginal probability is a sum of two products, okay? And the proof exactly reflect internally in a unique object the computation of the probability, and at the same time the building of the graph, okay, and also the marginality given by the sum of these two branches. So at the same time, simultaneously, we are computing marginality, we are building, we are checking that is a DAG, okay, and okay. Oh, what's the name? 4 minutes. Just as a conclusion, I would like just to say that this kind of language are completely inspired by proofnet of linear logic. Okay, actually, we use this syntax currently instead of this one, which is a graphical syntax, and a proofnet quotient, a class of derivation of the same goal. Okay, this is a way, a compact way to talk about all the possible way to compute this probability with this goal. So it's completely asynchronous, completely parallel way to compute. It's completely graphical, and in this dashed line, I try to just give you a flavor of how describe the method. Are just links. Okay, method is a links in a graph, and this is the example for the marginal probability. Okay, this is in the sequence calculus style, is a tree. This is in the proofnet style, a graph, and we are working with graph proofnet for talking about graph Bayesian networks. So the same status. Okay, and okay, I think that's all. We can also try to implement. We want to just check that there is power enough in terms of complexity, and we are right now implementing all the algorithms that we know, like click tree, junction tree, or variable elimination, belief propagation for Bayesian networks. Okay. Grazie. Thank you.